Thank you, Floris, for your presentation.
Thank you.
So we move forward with the last presentation coming from Guillermo Carpintero from Universidad Católica, Universidad Carlos III de Madrid.
Okay, thank you very much for the introduction. And this is about terahertz photonics for fast communications, and I will try to be fast on the presentation. Not sure if I will make it to the original schedule. Okay, so this is one of the applications for which photonics has been pioneering in the development of high-frequency systems, especially in the terahertz region. The agenda for today is this, and you're lucky that today is Monday. But first of all, I would like to present the team that made all the results that I will present here possible. And actually, what we are a team of engineering doing engineering, and basically we are trying to change things with the developments that we do. And what we are doing is developing terahertz systems. And terahertz systems is actually the terahertz region is actually here, and you can see it's between electronics and photonics. So we are the black sheep everywhere we go. Basically, why we want to develop terahertz systems? This is the first question I try to answer. And you see, the first answer to this, and I don't know if you would need any more, is that because it provides bandwidth. And bandwidth is the real state of communications. It's like, you know, the higher the space that you get when you buy a house, the cheaper it gets. Because actually, the regulator bodies, and especially governments, didn't know and didn't expect anyone to be able to communicate at these high frequencies. It's quite difficult, as I will show you. So it's not yet, there is no cost for using this bandwidth, especially above 275 gigahertz. So it's cheap. And when I mean cheap, at some frequencies, at some bands, it's even free. And actually, you can see that this is where communications take place. So you have to fight against many interfering emitters. But as you move up, you get more space to fit your bandwidth, your signals, and actually there is less people. So that means that you are the only one emitting, which is very good, because I will show you as well that there are some problems. There are more reasons why to use these high frequencies. Basically, they are very directive. This is the beam divergence. You know, it scales over frequency. That means that the higher the frequency, the lower the beam divergence. That means it's very secure communications because you are not radiating outside of the target. This is one of the advantages. Actually, you reduce the interference between the channels. And that allows you to get multiple channels. On top of this, this is if you maintain the size of the antenna. You know, the diameter of the antenna becomes larger as you increase the frequency. But if you take this in the other way around and you say, okay, I move to higher frequencies, so dimensions get smaller, that's correct. You can miniaturize your systems. This is what the first wireless link in microwave, and you can see the horn antennas up here. They had to use a house to hold them. And if you move, this is what the frequencies, the antennas, horn antennas, same type of antennas, look like at millimeter and terahertz wave frequencies. And as you can see, now we are talking about millimeter size dimensions. So that's a significant improvement. So you can choose whether you want to trade directivity or size. Okay? You have this possibility. More things, it's regulated. So I told you it's free, but that doesn't mean it's the, the Far West. It means this spectrum has been regulated, and that, as I will tell you, gives peace of mind to the end user. At the end, you have a company that wants to put a communication link. Sometimes it's for ad hoc communications, private networks. They want to be sure that they can transmit at those frequencies, not forbidden by law. And there is now a regulation for this. Okay? And there has been, this is an IEEE norm to communicate at 300 gigahertz. So there are many reasons why this is interesting, okay? But as I told you, it's also challenging. And I'm just going to show you some of the challenges that we face when we use these frequencies. This is one of the articles, Terahertz was hype some years ago. And suddenly it just disappeared out of the research. And actually, this article was just an expression of why it became a low topic, a low interest topic. And basically, it's because this article just highlighted some of the problems without mentioning some of the solutions to those problems. And this is the main problem. Okay, when you talk about people and tell them, okay, I'm using terahertz frequencies, basically, they immediately associate this to loss, very high loss. And it is very high loss. I mean, as I told you, we increase the frequency, dimensions become smaller, and actually, communication paths become farther away. And that means that your free space loss increases with frequency. That's a problem. And just to give you a size of the problem, I just calculated the free space loss for 120 gigahertz, okay? And this was 134 dB. Sorry, because of the rearranged slide set, okay? These losses were not taken into account in the previous paper. They were only complaining about the attenuation, atmospheric attenuation. And you see the scale here, it's also in some respectable dBs per kilometer. On top of that, you have some peaks in which the atmosphere absorbs even more than it's expected at the frequencies sidebands. Okay, this is, looks difficult, and is even more difficult if you think about the losses on guided media, on coaxial cables. The coaxial cables at terahertz frequencies, okay, at 100 gigahertz, just a rough same number as before, the cables, if you put them on kilometers, because here just that is for a cable of 100 millimeters. So if you move to some kilometer range, okay, that number is, okay, forget it. There's nothing we can do, okay? So it's in this, when we think about terahertz, we are thinking about wireless communications, but when you think about how do I carry that frequency to the antenna, if you think on a guided media, you're done, okay? The only solution that the electronics has is rectangular waveguides. You see, this is coaxial cables and the frequency range they cover with these losses, okay? The alternative is just rectangular waveguide technology. And if you look into it, I just highlighted that it covers a fixed and narrow range of frequencies. So if you want to change your frequency, you have to change the whole pipes taking the signal to the antenna. And actually, if you see, when I say pipes, it's what they look like. It's just a hollow waveguide, metal waveguide. Okay, so you could put water into it, and it would just slide down to your circuits. Okay? So, losses here, well, compared to this is piece of cake. And that's why in electronics, high-frequency electronics, they basically call it plumbing, okay? Because this is what they use. But the frequency, this banded frequency nature of the waveguides, it's a problem. And that's where we use it, if we want to use these high frequencies. I'm just showing also that even for above 10 gigahertz, you start having a reasonable amount of losses. You have to bear in mind that still this was millimeters. Okay, that's one problem, the loss. The other problem is that, okay, if I have a powerful source, that wouldn't be a problem. But I don't have a powerful source. Actually, these are the types of sources that we have. And basically, you see, these higher power sources, they are room-like structures. Okay, it's quite big sources. The integrated ones, of course, are down here. And they emit up to a milliwatt. Usually they are in hundreds of microwatts, okay, if we are lucky. And so basically, and this is actually a quote of the paper that I show you. And basically what pointed out is that the problem is in the source. Okay. This is quoted. They are really hard to build, and especially if you want them integrated. This is a mixture of photonic and electronic sources. This is all the sources that there are. Okay, and photomixers are down here. They are, the less powerful of the family. So some sources that you wouldn't even consider. Still, they are used. Okay, but the other problem is that, okay, they are difficult to build. Well, they are even more difficult to characterize. When you build a circuit, you actually want to measure how it performs. Okay, and usually you take a VNA, vector network analyzer, and generate frequencies and measure the amplitude and phase of the reflected and transmitted, and you characterize your system. Okay, when you move up to the millimeter wave range, I told you, you have a banded nature because of the rectangular waveguides. These are the sources, the transmitter and the receiver, port 1 and port 2, with rectangular waveguides. But it's not just 2 that you need. You need as many as the frequencies that you want to cover. That's another problem. Okay, actually, this is not just the end of the problems, because, of course, you have your rectangular waveguides from the emitter and receiver, and you actually have to inject the signal and get it out on pipes. Okay, and you have to put the probes on your chip. You look at that and say, okay, that looks difficult, and it is. Because I told you, the higher the frequency, the smaller the size. So your probes start becoming smaller, and when things are smaller, they can become very fragile. And when you land your probe, you basically pray that the probe doesn't break, because these probes are not cheap. The bandwidth is, but the equipment is actually quite expensive. So there are lots of problems. And on top of that, the contact is so, the measurement is so sensitive to the contact that you actually don't know what you are measuring, the performance of your chip or how well you landed your probe on the chip. So it's an instrumentation problem. And actually, with all of these are basically all the problems that I wanted to highlight. And of course, there's nothing better than a good challenge. And that's why we are doing this. But of course, we decided, okay, we must do this with a reasonable approach, and that's why we selected photonics. Okay. Actually, how we are dealing, we are actually developing photonic probes to generate these high frequencies to probe into the chips. And this is the project that we just started with Anritsu. It's so challenging that it's a future and emerging technology EU project. Okay, there is a lot of information in the website that is barely readable here. Sorry for this. You can ask me. As I told you, there are two main approaches. It's the electronic and the photonic. And basically, this is basically like going uphill. You multiply low frequencies into higher ones with electronic mixers and multipliers. So this is the uphill. And then we have the downhill, and is the optical down conversions. You have frequencies in the optical domain, 193 terahertz, and you basically down convert. Usually the downhill road seems much nicer to take it and try to be successful. And it has one main advantage. It allows you to beat the wired propagation losses. I told you that the propagation losses on wire media is outrageous. You wouldn't even consider it. Okay, photonics allows you to do it. And that's why, that's one of the first applications that gave rise to the field of microwave photonics. It was the low propagation on fiber. This is a comparison of the coaxial cable and the fiber. And of course, in losses, it's incomparably better. You wouldn't think on putting a coaxial cable. You would think of putting an optical fiber. So when you move into higher frequencies, you want more of this and less of this. You want to put your optoelectronic conversion when you actually generate the high frequency electronic signal next to the antenna and reach there with fiber. And that sort of is what we do in optical communications. We just move high frequency through optical fibers, and we transmit just at the edge where we need the wireless signal. And actually, photonics allows you to do this. Actually, these are some of the sources that are being developed. There are many sources, optical sources, to generate high frequency that have been built with discrete components. But there are some problems because, as here mentioned, the fiber is a sensor. And that means that it interferes with the phase. And here we care when we generate high frequencies by mixing optical signals, we care about the phase at which they arrive at the photomixer. And that's why integrated photonics is a very nice way, because you actually combine the wavelengths on chip, so phases will change, but accordingly on both optical signals, and you reduce the effect on the mixing. Actually, we developed this this is a transceiver. Actually, it's a transmitter. It has two DFB lasers, combine them on chip, optical modulators, and high-speed photodiode in a single chip. That was a project that we finished a long time ago. And we demonstrated that photonics, integrated photonics, allows you to implement high-frequency sources, even with the photodiode on chip. Actually, you could cut it at any point in the optical path, put a fiber, and you would be able to transmit this down to the remote antenna unit. In the remote antenna unit, that's where you want to have an optoelectronic converter. And these are results of photodiodes. As you can see, we can get up to the milliwatt, 0 dBm output power today with photodiodes. The higher the frequency, okay, you have the 20 dB per decade roll-off, okay? But we can work to solve this, actually, with the antennas. That's something I told you before. You can reduce the size of the antennas. Reducing the size of the antennas allows you to put more antennas on a smaller area. And that's it, to build an array. And with an array, you can actually do beamforming, so you can concentrate the energy of multiple emitters and increasing the gain of the antennas. Because when I told you, okay, we have so much losses, that's what you compensate with the antenna gain. And that's why it's important to move to higher frequencies, because then you reduce the size of the antennas that you need. And actually, this is numbers of a link budget. And you can see here, this is distance, and this is the antenna gain that you would need to cover the losses for a given range and still get reception. And as you can see, it moves, when you go, it's included here, a kilometer, which is the goal target for these frequencies. And actually, for a kilometer, you would actually need 40 to 50 dBi antenna. That's usually a Cassegrain antenna, if you just want to have one element. They are big, and it's difficult to build an array with them, but it's certainly possible. The ideal would be actually to cover up to 10 meters, 20 dBi. This is fairly possible today. And as I told you, what we would need is an array. And we are working actually to develop this array technology. What you can see here is our first demonstrator with one antenna element. This is a Vivaldi antenna that covers the whole E-band here. So this is the emitted power. This is measured with a calibrated power meter, absolute power meter. So what I'm showing you here is actually the power that we were able to transmit. And we are working on the assembly of the photodiodes together with the antennas. Because, as I show you, the antenna is one of the crucial elements. And what we have to avoid is the losses at this interface. Because what you see here, it's an optical fiber. This is where the light comes and generates the terahertz. And actually, we succeeded to demonstrate an antenna array. This is a two-element array. This is the simplest array that you can make with two elements. You can see that actually the two elements are alike. So this is the response of the frequencies when we emit with one or the other, and measure the emitted power over the entire frequency range for which this antenna was designed. And when we use the two antennas at the same time, and we double the frequency. So you have the 3 dB increase in the power. So now, this is a Eurocoin, so you can actually see the size of this two-element array. We also use 100 yen, because we are collaborating with a Japanese group on this, and we were hoping, it's one of the markets for terahertz. They are opening, actually for the Tokyo 2020 Olympics, they are opening higher frequency bands at 118 gigahertz to actually accommodate 8K distribution, wireless distribution for the Tokyo 2020 Olympics. Other applications that terahertz had, just to finish with some of the applications, it's the spectroscopy. In the terahertz range is where molecules have resonances. And that allows you to identify compounds by the absorption peaks at selected frequencies in this range. So actually, what they need is the optical generation, time delay, and photomixers. This is the optoelectronic conversion. We are actually, the phase here is critical. And the phase delay is also quite a challenging element. And we are actually working to implement this on a chip. Basically because you can see that you usually don't have this very far apart. This is not a communication system. Actually, what actually you need is this is usually done on fiber, and this is a mechanical time delay, optical delay. We are actually we're working to integrate this on a chip. It's not very different from a communication system, but phase is actually very easy to control on a chip. The other application that we are looking is, of course, making use of the wide bandwidth in the terahertz domain. And the application for this is now it's called beyond 5G. After the telecom carrier companies have redefined what they want 5G to be, the high frequency at millimeter waves, it's been moved to beyond 5G, and some put already the name of 6G. This is where the regulations at 300 gigahertz, they are meant for 6G systems. It's because we can achieve this, we want to achieve the convergence of wireless and fiber optic, basically to achieve the wide bandwidth sites. And what we actually are aiming to develop is the small cell sites to give wide bandwidth coverage to the users. Users will not need millimeter wave frequencies to communicate with the small cells, but small cells will need to communicate to the entrance to the core network, to the edge of the fiber network. And this is where we see the applications of these systems will be. And actually, moving from fiber to wireless, it's a key point in the macrocells to distribute to generate the high frequencies at this point. And with these frequencies, be able to drive these small cells. And this is what I wanted to leave things and just give you the floor to ask as many questions as you want.
Questions from the audience? Jose.
Very impressive, Guillermo. I followed your previous project, that one you said that you finished a long time ago, and that was already a big achievement on the integration. But we've been talking about terahertz for FSO already for a while, for as long as we know each other, which is a long time. I see this slide now, which is beautiful. Can you comment on the real challenges that we have to convince the activities in smart cities, to convince the companies who are trying to make this free space communication in cities with change of environment, change of weather, change of temperature, change of dust conditions? Can you comment on the advantages of terahertz on this?
Yeah, that's a good question, because today there is, even in space communications, they are looking into free space optical communications. And when you think about the distance that they have to cover and the losses that they are, actually the issue is that the free space optical communications use the windows in the atmosphere. And that's why they are usually preferred. But one of the things that is not usually taken into consideration is that you just don't need the atmosphere to be transparent. You need to be stable. Because when you have a channel, you have to point from the transmitter to the receiver. And the atmosphere has different layers and behaves differently. And especially when there are temperature gradients, and that misaligns or interferes with the path that the waves follow. And it's more serious as the frequency increases. So when you move from terahertz into optical, which is several orders of magnitude of frequency increase, the atmosphere is very aggressive, or has some of additional problems. It's not just the loss. It's how the waves propagate through the atmosphere. And the problem is the beam wander. That's the name that the atmosphere changes the alignment where your wave ends. At free space optical communications, that's a very serious problem. In the terahertz, you have a more soft, it's a more relaxed in terms of misalignment of the link due to the atmosphere changes in temperature and humidity. So it has, terahertz has this advantage. It's easier to point, to maintain the pointing between the transmitter and the receiver.
Nice that you mentioned the space. As maybe you know, just after summer, we organized the EPIC meeting on new space at the Space Agency, and we had there Airbus, who defined the specs for the Skylight project. So actually somebody in the audience from Toptica asked them about the terahertz, and they were extremely negative on this. That was the first reaction, were negative. Yes. And then they talk about the specs, which actually they had defined the wavelengths. Is that in your new activities very linked to space, is that a challenge or an opportunity?
That's an opportunity. Because when I saw this atmospheric absorption, this falls down at the visible light, which is in this region above. But that's as long as there is no humidity, no clouds. When there is already some satellites, the small satellite that is using optical communications. They have built a laser and they communicate. They did the DLR, the Deutsche Luft- und Raumfahrt Institute did some studies. And if you look at the passes of the satellite over the base station, they have blanks because it was covered partly clouded, and they couldn't establish a link to communicate with the satellite. And it's always weather conditions, and that's not an issue for the terahertz. Because I already showed you how much losses we have to overcome, and we are working with this. We are working to overcome this with arrays, and the array not only allows you to do beam forming and increase the power, but allows you also to do beam steering. So beating the power, you actually gain in the directivity, control of the directivity of the beam, which is actually one of the mandatory, it's mandatory for any communication links. You have to have some beam steering mechanism. And in optics, that's not trivial. Still is an issue. They do it mechanically. They don't have electronic steering in optics yet.
Any other question? So I think it's time to lunch.
Yes.
Thank you very much.
You're very welcome.
Guillermo, for your presentation.
Just before going to lunch, let me show you again. Let me show you again the different B2B meetings that will take place after 2:30, okay? To understand the table at 2:30, Íñigo Artundo and Eduardo Margallo, for example, or Pascual Muñoz, and the people from Chip Nanoimaging, Mike Beunder and Jose Pozo, people from Alcyon Photonics with Pink Cat from Technobis and Gaia Sardiello from Fila with James Weber at Panasonic. Every 30 minutes we will change the groups. You come with me to the red cube and we will go to the fourth? To the fourth floor, and that's it, and take a look about the different B2B meetings, and if you want to maintain a meeting with someone who is not in the boxes, please tell me. Okay? Thank you.